Its second lecture will continue from where we stopped yesterday.
Yes, so thank you. So yesterday it was basic introduction, setup of the program. Today I will focus on a particular way of extending the sigma model in such a way that they have something called supersymmetry. I'll show you what it is, and I'll try to be constructional in the sense that I will not address sort of the deeper meaning and philosophy of the topic, but show you how it actually works, how you actually crank the handle and it comes out. So let me remind you of the setup. We have a d-dimensional, small d-dimensional manifold sigma that is mapped into a big d-dimensional manifold M. And today, I'll mostly be interested in little d being 2. Okay, and then I was reminded, or not reminded, but I realized that yesterday, in some places I said that it's 2D, right? Which means I meant 2 dimensional. And then if you say d is equal to 2, so somebody might say that 2d is equal to 4. So just to make sure, today little d will be 2 all the time, okay, which means 2 dimensional. So I'm sorry about that. Here we might have we have metric, and today this metric will be flat. And here on this side we might have a non-flat metric or a flat metric, but some arbitrary metric g. We may want to add this 3 form that we were talking about here, and then we will see there may appear additional structures here. But the essential thing that I want to add today is more structure on this side. So a physicist would say that we add fermions on sigma. There's one more thing I need to set down. One more thing I need to tell you. So here, I'm using coordinates which have the same notation as the map. So I call them phi. Here I'll use coordinates psi, but today it's useful to use the line coordinates that I introduced last time. So they are defined as in this way, possibly with some factors. And in those coordinates, the metric is off diagonal. Okay, so this is just a basic setup. Now we have these formulas. So what are these guys? So they will behave as something transforming in one of the spin bundles on sigma, which is indicated by this plus index. And tensor the tangent bundle, the pullback of the tangent bundle on M, which is indicated by the M index. And they will be anti-commuting, as is standard in physics when you have fermions. So one way that people indicate this is to say that it's not a tangent bundle, but a parity reverse tangent bundle. But that's just a way of saying that they are. Right, so psi plus M. And of course, again, we need to specify the action. That's the third ingredient in the whole story. So the first term is just what we were discussing the whole time yesterday, written in these new coordinates on the bond sheet. Right, so this is the term we had yesterday when I wrote it in arbitrary coordinates. But now I also need the fermions. Yeah, these symbols are derivatives with respect to the black component. So to be completely, absolutely as simple as you can, let me choose G to be the Latin cosmology. Right, so D plus is derivative with respect to psi plus. Yeah, and this funny notation with the double plus is to not confuse it with the single plus. And well, actually, this transforms as a tensor product of the spin bundle with itself, so it makes sense in a more deeper way. But okay, let's take this as our action. Yeah.
The tensor product is pretty complex numbers. So do you have any complex structure that you chose, or what's
these fermions are real.
So what's the rank then of this S plus tensor?
It's a line one, real line one.
So S plus you're taking it to be a real line one.
Yeah. But that makes that gives you some strong constraints on what sigma can look like. So usually at this point, when you do this lecture, you have to make a choice, right? So if you want to have your size to be real, the metric on sigma to have signature 1,1, right? These two things are connected. Then you really should imagine sigma to be a cylinder or or just a strip. You couldn't have more complicated topologies because you would get into problems with the line model doesn't exist, or you can't globally choose a network with the signature or whatever you want, the way you want to say it. So I'm going to stay with this proposition. And so if you're uneasy about this, just think of sigma as being a cylinder all the time. The other choice you can make is to do weak rotation. The metric will then have signature 2.0, but then the spin bundles will be complex. And then at some point, to make contact with the physical model, if that's what you're interested in, you would have to make some kind of, impose some kind of reality condition somewhere. Okay, so both ways are fine. They have their own problems in some way. I chose this way to work, and then you should imagine this to be a cylinder.
Sorry, the second term in action is path?
Yeah, sorry. Thank you. Okay, so this action now has a symmetry. We know from yesterday that symmetries of the action are connected with interesting geometrical structures on M. So let me first show you how the symmetry looks like. So infinitesimally, change in phi looks like this, and the change in psi is this, and you can verify by explicit computation. It's not hard that this is the symmetry of an action.
What is epsilon minus?
Yeah, sorry, good. Yeah, that's what I was going to say. So epsilon minus is so it's the infinitesimal in this case I did the quotation marks parameter of the transformation. So when you verify things, you work to first order in epsilon. There are no second order terms anyway because it's Grassmann. It plays the role of the parameter transformation parameter that you only have in really good transformation. But the fact that it's Grassmann is important because it gives you some important minor signs when you anti-commute it with the fermions, other fermions. Yeah, so this is sort of the archetypical, the absolutely most basic supersymmetry that you can think of. So the super means that fermions and bosons are mixed. So boson transforms into fermion and fermion transforms into boson. And yeah, good. I did erase it. So we can add fermions transforming in the other spin bundle also. And again, they will be completely analogous transformation, but now with the plus fermions replaced by minus fermions. Right, so this is now these two transformation parameters are different. We have two supersymmetries, or in the two-dimensional language, one counts supersymmetries mixing plus fermions and bosons differently than supersymmetries mixing minus fermions and bosons. So this one tells us that we have this symmetry, and this one tells us that we have this symmetry. This symmetry, in fact, survives even if we now make this metric non-trivial or non-flat. But there are some additional terms you have to add that comes in and you can see that they are necessary. You have to put them in. So here, R is the Riemann tensor of the manifold M. And let's say, for instance, this derivative was replaced by something which is a covariant derivative. So what I mean with this is this thing where now I have a Levi-Civita connection coefficient. And similar to here, but with pluses and minuses exchange. Right, so having a non-trivial metric of M, we need to fix up the action a little bit. We also need to fix up the transformation, the supersymmetry transformation a little bit. So. So there is an additional term that we need to add, also, and then fixing things up in this way. supersymmetry survives even in the presence of the
This cannot be right because we want
Sorry?
the transformation of sign minus cannot be right.
Cannot be right.
There's no epsilon.
There's no epsilon.
No, it's the determinants of psi minus, the ground is asymmetric.
Why not?
There is non-interactive H.
No H so far. Sorry, why is this wrong?
Maybe I'm mistaken, there must be the derivative of scalar rather than
Why?
one of them.
So how can, there's no,
Maybe
if you want to respect dimensional analysis and Lorentz properties, there's no derivative of scalar. You can have it.
No, but I think confusion, I mean, you use the same notations, presumably you should put delta 1 or delta 2.
Okay.
It's too, I don't know.
Okay. Does this help?
And then,
Yeah, question.
If psi is your value, how can you add I in the transformation?
But this is a information operator.
Yeah, but then you make it complex of I.
no, that's the whole point, to make everything real, but as you know in quantum mechanics,
Yeah.
derivative everything is equal to totality.
Yeah, to make it easy, but then you add the imaginary part of psi.
Right, but reality conditions on framework is also something.
Yeah. So what is the reality condition then?
It's very determined when you conjugate,
Right,
you
so-
change the order,
Yes.
and that's exactly what.
Right. So, what?
It's real. Just over you have
Yes.
I mean, reality is done in quantum mechanics using permission computation, not complex computation.
Ah, okay. So, okay, the real in that sense.
Yeah. So, I mean, I'm going to come to this later by trying to write down the most general transformations to look for new supersymmetries or other supersymmetries. But so I'm going to say that for this supersymmetry, there's nothing I can add here that looks different, actually. Okay. Yeah. So,
sorry.
Yeah.
So for your covariant derivative, so is it a covariant derivative on what sheet?
no, it's not a covariant derivative. Definitely not on the one sheet. Like the Chilita connection coefficients are the tangent space, the target space level Chilita symbols. But you could say it's a pullback on tangent space covariant derivative. Okay. Right. So, so the next question. But the only thing I did was add the fermions. If I had plus fermions, I did one supersymmetry. I had minus fermions, there's another supersymmetry. So now you can ask, under what conditions will there be further symmetries of this type? So let's think about how the most general symmetry a trusty physics tool called dimensional analysis. Lorentz transformation properties, and the fact that it has to be supersymmetry, so it mixes bosons and fermions. So the dimension of let's say a derivative, I will, well, it's 1 over a coordinate, so if you use length dimensions, this has dimension -1. So this bracket means dimension. The dimension of a fermion we can figure out from the action by seeing that there is a measure which has dimension 2. There are 2 coordinates, they have dimension length. There's one derivative with dimension -1. The action has to be dimensionless, so 2 fermions have to have dimension 1, and 1 fermion has dimension, -1. Yeah, so this has dimension 2, this has dimension -1, so the 2 fermions have to have dimension -1. And 1 fermion has dimension -1/2. The dimension of a scalar, you can figure out from this term. Again, we have this has dimension 2, this has dimension -2, there are 2 derivatives, so scalars have dimension 0. And to make things work, we have to count the epsilon as having dimension 1/2. So now we have something with dimension 0 on the left-hand side. So we have to write something with dimension 0 on the right-hand side. So this has dimension 1/2. That means that the rest has to have dimension -1/2. So I mean we can have only 1 epsilon. So we can't raise dimensions, we just lower dimensions here. If we add a derivative, we have already gone too far, so we can only have 1 fermion. But we can have as many bosons as we like. So the only way we can change this, or make it more general, is by putting some matrix, which will be a function of all the phi's, possibly, here and then the fermion. This has the right properties. Lorentz indices add up to 0, so that agrees to the left-hand side. And if this is a tensor on M, this is a valid ansatz. So doing the same thing here, the same kind of argument tells us we can have fix up the term we had before in this way, but there's also a possibility to add a new term here. So instead of having a derivative, we can have 2 fermions and call this this. And what can we add here? Well, think about it. Again, we have these a term of the type I wrote, but again we put here some arbitrary tensor on M. So this is the most, I claim this is the most general thing you can have. And then you can ask, what should these tensors, what kind of relations they should satisfy for this to be a symmetry of this action. Right, so you go ahead, you plug it in, and you get a bunch of relations. So what pops out immediately of these relations is that this tensor I has to be correctly constant on n. This is a relation on n. Right? Another relation on n, sorry, this is not quite what you get. Jump ahead a bit. I, G, and J. I is this tensor, J is this tensor, and G is the metric. Has to satisfy a relation like this. You work a little bit more, and you find that M, this tensor has to be related to the connection coefficients in this way. And M similarly has to look like this. Right, so you get a bunch of interesting looking geometrical conditions on these objects that I postulated or were part of the ansatz, involving ij, involving all these objects. Okay, there's
So we got the I plus one minuses, or is it I transpose is the first one, right? It's
yeah. So if you want, depends if you're, this is what I mean.
The last one is an N, right?
Yeah, and last one is an N, which I changed. Of course, I forgot that I changed it. Last one is an N. Then there's one more relation that you can impose. Let's see if I want to. Yeah, that's a reason. Here. Which uses maybe some knowledge that I haven't talked about or I'm not going to talk about. So one characteristic of supersymmetries is that when you take two supersymmetries and you take their commutator, they give you the structure of a superalgebra, which in this context means that you should get something like epsilon 2, epsilon 1. Right, so I'm taking two transformations of this type. The parameter of the first transformation I will call epsilon 1 minus, the second epsilon 2 minus. This should be. And this gives me another relation ij is equal to j I is equal to 1.
Is that epsilon plus and minus or epsilon minus 1?
These are,
This is what you call the
so these are the epsilons are the transformation parameters. Now I'm making two different,
for the same minus.
the same transformation but two different transformations, and I take the combination.
So here you mean on-shell closure.
Pardon?
Here you mean on-shell closure. You need to impose equation of motion that closure.
Why? Equation of motion of what?
Fermat.
Oh, you mean when I do, yes. In some, well, right. In some of the commentators I will need to do that, yes. So, I'm cheating a little bit here, just pretending that this goes through. So this is something that happens sometimes when you have supersymmetry, that the algebra doesn't close off shell, that it closes up to equations of motion, but that's a well-known thing, and the solution to that is to add auxiliary fields, which will realize the symmetry. So I skipped that bit, but so morally speaking, this is correct. Right, so now the transformation here, I can actually put I inverse instead. Okay, because of this relation, J and I are inverses of each other. And here, I can put these I gamma terms. Minus I. I gamma, I mean appropriate indices in the appropriate places. So that's, yeah.
Is bracket the commutator there on the top? Is that symmetric or anti-symmetric in 1 and 2?
Symmetric.
So I would have expected that guy to be an anti-commutator. So if I shift 2 and 1,
Yeah,
I would expect to see the same thing. An epsilon 1 and epsilon 2 commute, anti-commute in your picture.
It's because I included the anti-commuting parameters. Right, so if you're looking at the algebra, so the generators of these transformations are anti-commuting objects, and their natural bracket is an anti-commutator.
Right. So therefore I expect the right-hand side to be symmetric, not anti-symmetric.
But then, if I include the parameter together with the generator, then I get something which is commuting. That's why with the delta I mean this. So that's why I get the commuting.
Okay, so your answer is, so you're taking the epsilon times your generator in your real.
I mean, there are two conventions. One for physicists like they put, parameters and delta is even, but you could equally not to put parameter epsilon and put a spinor index on delta, and then it will be odd. It's totally equivalent, but due to historical reasons.
So delta is even in your pictures, not odd.
But all questions of this type are very good to straighten out confusion and sort of normalize different languages. So this is the transformation. Does our original supersymmetry satisfy these conditions? And that's the first question. Certainly does. If we choose I to be a constant, a unit matrix, then this is definitely true. This is definitely true. It just tells you that G is equal to G. we didn't have this term in the transformation. That's how come this stays here? Well, if this is a unit matrix, you'll just get PQ here and the anti-symmetrization on this because of the fermions. But if you put gamma here, it's symmetric, so it drops out, which gives you a hint that if we had a torsion full connection, this might still be there. Right? And this term reduces exactly to the term we have in case I is identity matrix. Okay? Okay, but if it's right, if it's not a unit matrix, what does it tell us? Well, we have this term, which is nice. If we take this, solve for J and put it in here, we get there seems to be some lines. Yeah. Inverse. So this is inverse, right? Now, the final piece of information that you need is that you two different supersymmetry transformations, not the same, but two different ones, should commute. So if you suppose that, thinking one to be the one with the I, and the other one to be the original one we had, then you can actually deduce that I should square to minus 1.
So it comes from what at the end?
Pardon?
Comes from what at the end?
This identity. Well, so take this was the anti-commutator of two supersymmetry transformations, but the same one. But now we have two of them. There's one supersymmetry transformation with I, and the other one the original one we had. And I want them to be independent. Right? Not independent. How should I say it? I want them to commute. So each of them by itself satisfy their own supersymmetry algebra. Gives a supersymmetry algebra which is closed by its own weight. And then we have another supersymmetry algebra for Galileo. So the commutator of these two different supersymmetries has to commute, but that gives me this relation. So this tells us that I is not just a tensor, but it's an almost complex structure. This tells us that G is Hermitian This tells us that I is integrable so I is a complex structure. So, existence of the first supersymmetry followed just from adding fermions. Existence of the second supersymmetry requires some additional structures on M. It tells us that M has to be a complex manifold, there has to exist a complex structure on it. Sorry?
It has to be Keller.
It even has to be Keller, yeah. So, from this relation, you can show that from the hermeticity follows that this is a two-form. And from this relation follows that the denominator is closed. This is the Galilei position. Yeah.
Why were you forced to have only psi blast, so the fermion blasting is the other one? I could have thought of that on the other hand I could have a tensor on both spinor bundles and not just one.
So I have psi plus and I have psi minus.
No, right, but in the first situation I could have added something that depends only on psi minus and look for the most general there. And I may find some other challenges.
Here, you want some psi minus.
Right.
Well, I'm counting the Lorentz indices here. So epsilon, the parameter transforms in S minus, and the fermion transforms in S plus. So together they form a scalar, which is consistent with the Lorentz properties of phi. So that if I want to add a psi minus, that necessarily forces me to introduce another parameter, which gives me the whole. This supersymmetry can of course be copied to the other case, to the thing which rotates phi's and psi minuses. Now this is something which is special to 2 dimensions, that you can treat the psi pluses and the psi minuses independently. In high dimensions, that's usually not the case. You will have to include both in the supersymmetry transformation. You can't have independent left moving and right moving supersymmetry. That's a notation that I will have to explain what it means. Right, so if you want to say it with one word, having the existence of one additional supersymmetry requires the target manifold decay. So one can go on. What about if there exists, let's call this I1, and there exists another one, I2, but they both have to satisfy the same conditions as I told you. And then one can require that the transformation with respect to I1, or one should require the transformation with respect to I1 commutes with the transformation using I2, which gives new relation this. Or if you wish to rewrite that I1 and I2 anti-commute. So they're both complex structures and they anti-commute. Well, that means that you can construct a third complex structure satisfying exactly the same conditions. So if you assume one extra supersymmetry, you automatically get 2. And if you analyze all the conditions together, you will find that the geometrical requirements of N is that it should be hyperclear. Now, yeah, and of course this can be, I was looking at the epsilon minus transformations. You can do the same thing for epsilon plus transformations, and the equations are essentially the same, and the requirements are essentially the same. It becomes more interesting when we incorporate also the H field of M. So it can include the torsion. So far we haven't had any torsion. So you remember we did this by it's locally by using the two-form B. Now it turns out that you need to modify the other terms also. When you have this term, you need to modify this here. Here. And also here. Where now these connections, as you remember before, let me plus, and this was this expression, but now the connection coefficients are not the Levi-Civita, but the torsionful connections that we encountered last time. And the torsion is given by the three-field connection. And again, you can play this game, and well, essentially, all the calculations go through, except that you have to put the torsionful connections here. And
double minus is the
Sorry?
same. Repeat double minus. Double minus.
minus, yeah. This is
Same as plus.
yeah, this is minus.
Oh, okay.
So one has
sign,
torsion
sign.
Plus or minus
Okay.
is the Levi-Civita plus minus
Fine. Okay.
H. And so the calculation goes through, but you have to put in the torsion in the correct places. So, for instance, instead of having, well, you have, let's call this I plus. So I plus is still an almost complex structure, but instead of being covariantly constant, it's covariantly constant with respect to the torsionful connection. And then it's a little bit more tricky to see that this still implies that it's in fact integrable. But it's true. But, and this is also true, of course. G and plus. G is still a Hermitian. But, so you can still make a two-form out of the metric and I plus. but this two form is no longer known. So the geometry is definitely not Cayley geometry. But, okay. But it has, well, it's also been studied by many people, also people in the audience who are experts on this. So the requirement now on M for this to be true is that the manifold M is a so-called strong Kähler manifold with torsion, or SKT. Strong is the fact that H is closed. Kähler with torsion will be H non-closed. So in the presence of H, the target manifold is no longer Kähler but SKT. Yeah. Now, of course, you can play the same game as we did before. You have more supersymmetries. Again, you get one for free, and you get something which generalizes hyperkähler, which is called strong hyperkähler with torsion. So now I'm sort of out of time. I talked about half of what I wanted to talk about. So yeah, let me maybe just indicate what I wanted to say, or maybe I'll do some of it tomorrow in the morning. Before jumping into some applications of this. So the other stuff that I wanted to talk about was to introduce a formalism where you don't have to work to make sure that this is true. A formalism where you treat your sigma model in such a way that it's automatically true. So this is called superspace. And okay, so I wanted to present it in a way not very fancy, not thinking about any of the mathematical aspects, but as a tool to write down sigma models which automatically would have the specified properties. So instead of writing down nonsense for the transformations, seeing what they imply for the geometry, and so on, you can write down sigma models, and using this formalism, you automatically will have the right amount of supersymmetries, which means that your whatever you do to the sigma model, you will talk about the specified type of geometry. So if you write down the sigma model, if you in a superspace which will make sure that you have, let's say, 2 left-moving supersymmetries, 1 right-moving supersymmetry, you will make sure that this sigma model has a Tory space, which is SKT. Right, so this will make an interesting way. This is an interesting way to study these kind of geometries. And in particular, I wanted to illustrate this tomorrow by talking about quotients, where you can invent some tricks that you can perform on the sigma models. But the only thing you have to make sure is that you keep the supersymmetry, and then you will get new SKT. You can produce new SKT geometries from old SKT geometries. So that will be a sort of illustration of what you can do in the intersection between mathematics and physics with using the sigma models. So let's leave that for tomorrow. Thank you.
Are there more questions?
What is the definition of SKT?
What is the
Definition.
definition? So you have a manifold. There is a complex structure, a metric with its Hermitian, and the free form, such that
Closed free form.
pardon?
Closed free form.
Yeah, closed free form. This is SKT, right? Such that the complex structure is covariantly constant with respect to the torsion from connection. So there are alternative ways of formulating it. So you could instead you can see, for instance, if this is not closed, what is this? And it turns out, there's some.
I have a suggestion. I think it's better not to put H in definition. It's a Hermitian manifold such that d dc omega plus is equal to 0. So then it doesn't use H.
Okay.
It's equivalent.
DC is defined using the complex structure.
My question was, what if you had an explicit expression for the differential of omega plus? So, okay, I can see there is one. So at the limit, when you take b equal to 0, then you obtain your previous results. So
Yeah. So when b goes to 0, things reduce.
So it's a deformation. It's interesting.
Yeah.
More questions? If there are any more questions, let's take the speaker again. Before